get to rotations and translations, which is probably the most important topic in robotics, which is if you can master rotation and translation, then you can describe how things move. And if you know how things move, then you can do what is known as kinematics, finding velocities, or you can do dynamics, finding acceleration based on forces and so on. Okay, so first let's start with translation. Okay. Okay, so in robotics, what we do is we always have a frame which we fix to the ground and which does not move, and that's called the world frame or the ground frame. In this course, what we'll do is we'll write this as O, XO, YO, and this frame is called the world frame. Okay, it's also a fixed frame, it does not move. Then we have another frame which they call a moving frame or a local frame, which is used to describe the motion of any particle which moves. And also note that I've so far restricted ourselves to 2D motion. I don't have z-axis. So bulk of this course will actually be 2D motion. We can go to 3D if we need, but I will keep it 2D because I think that's good enough to learn the things in Lec1b robotics. So let's say there's a point C, and this point C is can be described in two ways. One is we can find what is the coordinate of C in the local frame, which is O1, X1, Y1, the local frame. And that point has, say, coordinates of XC1, YC1. So what I'll do is I'll explicitly show these things on the plot. This distance is XC1, YC1. So first of all, note I have X and Y denoting the X and Y distance. I have C as a subscript denoting it's for the point C. And then I have this superscript 1, which means that that distance is from the local frame O1, X1, Y1. Similarly, I can write the position of C in the world frame. So then the distance is going to be, this distance is YC0. Sorry, this should be this way. X C0. So if you have point C, you have the coordinates XC1, YC1 in the local frame. And then if you want to find the position in the world frame, you say XC0, YC0. This is in the world. So something to remember is that the point C doesn't change. It's the same point. However, we write it in two different ways. We measure it in two different frames. It's like if apple is an apple, but it's called with different names in different languages. Similarly, the point C is the point C, just that we write it in different ways in different frames. Okay, so just like you can write the coordinates of point C in I should have written this way. So this, we'll actually write it as C1, where the superscript 1 denotes local frame. And then you can write as C0 to denote the point C in global frame. Okay, the same point, but have different distances. Now we can also write the position of the origin O1 in frame 0. Okay, so in that case, what will happen is it's going to be this distance for the X, and that's for the Y. So let's call that distance as XO, YO. So if you measure O1 from the world frame, then you will have X0, Y0. You could also find the coordinates of the fixed frame origin, which is OO, with respect to frame 1. In this case, it's just going to be minus X0 minus Y0, as you can see from the distances I drew on the figure. Okay, so that's pretty much how you write translations. Things to remember is there's a fixed frame, there's a world frame, a local frame, and then the coordinates are written in terms of superscript and subscripts. Okay, next, let's go to rotations. Okay, so first let's draw the fixed frame. Okay, so when we say rotations, we are just talking about rotation without translation. So what we do here is we rotate this frame by an angle theta about the x-axis. So when we do that, what will happen is x0 will rotate to a line which we'll call O1, x1, and then correspondingly y0 will rotate to this somewhere like this, where theta is the angle between x0 and x1. So theta should also be the angle between y0 and the new y-axis. So again, OO x0 y0 is the world frame, fixed frame, and O1 x1 y1 is the local frame, which here has rotated. So what we can do now is we can again write the coordinates of C in two different ways. If you want to write the coordinates with respect to the world frame, then it's going to be this xc0 and yc0. If you want to write the coordinates with respect to local frame, we have to draw perpendiculars to x1 and y1. So this is going to be yc1 xc1. Okay, so then what's left is we need to now write the coordinates of point C in terms of, coordinates of C in world frame with respect to local frame or vice versa. So for example, we need, if you want to write x, C with respect to frame 0, okay, that is we are trying to write xc0, then it will be a linear transformation between xc1 and yc1. So there is something which when multiplied with xc1 and something multiplied by yc1, and when you add the two, you will get xc0. And we can do that using trig. So for example, here, if you see xc1 and xc0 make an angle theta, so we need to project xc1 along the x-axis or the world frame x-axis. So that will be cosine theta, and it's sound because the distance is positive to the right. And then if you want to, we want the corresponding distance along the y-axis, along the x-axis again, then we have to take this and project it along the x-axis. So it will be yc1 sine theta, and that will be negative. So why that's negative and positive, well, you can see it this way maybe here. So when you take this and you project it along the x-axis, get, sorry, okay, what's the best way to see this? Okay, I'm missing something in this figure. Let me try to redraw it. Okay, here's a point, and then this distance is xc0, and then this is yc1, xc1. I'm trying to find this distance. So if I need to find that distance, I need to project this line along. So this is theta. So then the projection is this line. So this is going to be xc1 cos theta, and that's what I have. But then I need to subtract out this part, and that part is If you see this, it's not very obvious, but that part should, I'm trying to see how that part is yc sine theta 1. See, anybody see it? I don't see how this.
Yeah, Professor,
I'm doing something wrong in terms of my.
No, I think you're right, but it's because of the angle that's made between the vertical axis with respect to us, and the tilted axis is the same theta, right? So
This one. No.
I guess it's tough to just to describe over words. But I think this is correct, no?
Now, it's, if I project it, it's going to give me this. Let me see if I can try to redraw it. See. No, I'm doing something wrong. Here it is. This is a mistake. So when I take this and I project it, this is going to be the projection. My bad. Okay. So, okay, I think I figured it out. Here it is. Okay, so when I project this line, along the x-axis, the projection is going to be this. It's going to drop the perpendicular. So this is incorrect. It's basically this much. That's xc1 cosine theta. And then if you subtract out this part, that's yc1 sine theta, because this is yc1, and then this is theta. So when you subtract it out, you subtract out this part, the same as this part, and then you get what I wrote down here. This is always tricky. Okay, so this is right. And then you also need to do the same thing for yc0. And I'm just going to write it down instead of drawing it there. It's sine theta xc1 plus cosine theta yc1, but you need to do a similar exercise to find that out. So what we can do is we can combine 1 and 2 as a matrix. xc0 yc0 equals something times xc1 yc1, and then we have cosine theta minus sine theta cosine theta. Okay, so that's basically what is known as a rotation matrix. And so what we'll do is I'll write this as C0 because that's the notation for position C in world frame, and then C1 equals a rotation matrix. Okay, and what we'll do is we'll call this rotation matrix as R10, which indicates the rotation matrix which relates frame 1 to frame 0. Okay, and the form is this way: cosine theta minus sine theta on the first row, and then sine theta cosine theta on the second row. Okay, so given this, we can also find C1, right, in terms of C0. It simply boils down to taking an inverse of this matrix. It turns out that inverse of that matrix is actually pretty simple. It's basically the transpose of R10. So it's cosine theta sine theta minus sine theta cosine theta times C0. So this is one of the important formulas. Just this much. And then the second important formula is the one below, which you don't have to really remember, because once you know the first one, then the second one just follows. Okay. Okay, so any questions on that? That's basically rotations. Okay, now let's come to the part where we combine the two. Let's do combined rotation and translation. Okay, question. What did you just did there with trig is the same as the Rodriguez formula? I think that the Rodriguez formula is different. The Rodriguez formula is more general. It has the translation part too, but I can just quickly check the Rodriguez.
I'm just kind of looking at Shabana's book, Shabana,
I see.
his book, and he uses Rodriguez formula for calculating the transformation matrix. So I just wonder if it's the same thing.
Is it the same thing? Because I think it's different. I'm just trying to search for Rodriguez formula, rotation formula. Okay, so maybe it boils down to the same thing, but my hunch is that it's different from the rotation matrix. Uh, I'm just looking at Rodriguez formula. I never thought of it that way. So the
Let me see if I can take a picture and upload it to Zoom, and you can take a look if you want.
yeah, I saw. I'm seeing it. I can see it. Maybe it just simplifies to the same one. I've never used it, but it might be the same.
Okay.
Okay, so let's do combined rotation and translation. So in general, what we're interested, and most times what happens in robotics is something translates and rotates, or rotates and translates. So in order to express rotation and translation, what you do is, well, let me draw a figure first, what I mean by rotation and translation. So we'll start off with the same frame, that is the world frame. We'll take the object and we'll say that the object first translates. So when it translates, it's going to move a distance along the x-axis and then along the y-axis, which will displace its origin. And then it'll rotate by an angle theta. So I'm just going to put both these things in the same figure. So let's say that it first translates. So when it translates, its new frame is going to be y1 prime, x1 prime, just like I shown the earlier reference frame for only translation. And then it will rotate by an angle theta. So now we have x1, y1. Okay, so I use the intermediate O1 x1 bar y1 x1 prime y1 prime just to show that intermediate point. So then we have the point C now, which is what we get after doing a rotation, a translation followed by rotation. This point has coordinates of xc1, sorry, yc1 and xc1. And so the way we think of this is that if you want to write the coordinates of xc in frame 0, then what you need to do is you need to translate it. So that will be x0, y0, and then there will be a rotation. So that rotation will come as xc1, yc1, and then the rotation formula. So what we did was we wrote down the position of C0 is the position of O10, which is the coordinates of O1 with respect to frame 0 plus R10 C1. Okay, and that's how we write combined rotation and translation. Okay, it's basically a superposition of the two things, rotation and translation. Okay, so that's just one rotation. Now, what happens is when we are looking at, let's say, a manipulator with two links, then we will have to do two of these rotations and translations. That's because there are two frames, two links. If there are n links, then you will have n rotations and n translations. So you will see that as you start adding more and more frames, the formula which I wrote down is going to become fairly complicated. So what we're going to do is that's going to actually motivate what is known as homogeneous transformation. So first I will sort of show you the problems with this notation, and then that will lead to what is known as homogeneous transformation. So both of them I'll put under one heading. To represent combined rotation and translation. Okay, so let's first see what the problem is. So I wrote down this formula. Okay, this formula is when this frame moves to O1, X1, Y1. Okay, now what will happen is if that point C undergoes another transformation from O1, X1, Y1 to O2, X2, Y2, then we can write the same formula, but now between 1 and 2. So the formula is O21 plus R21. It should be a superscript, then C2. So those are just two combined rotations and translations. Now, this is basically telling what is the coordinates of C in frame 2, and this is telling what's the coordinate of the point C in frame 0. Most of the time, we're interested in finding how the point C is with respect to the world frame or the observer which is fixed to the world. And so what we need to do here is we need to basically eliminate C1. So what we'll do is we'll substitute C1. So if we substitute C1 from the first equation to the second one, then we have C0 equals O10 plus R10, and C1 is simply O21 plus R21 C2. And so let's simplify that. We have O10 plus R10, O21 plus R10, R21 C2. Okay, so what we've seen here is a formula which had only two parts has now become something which has three parts to it. Okay, we can then keep doing this for n frames. So if there are not two but n frames, then we can write a formula for n frames by just continuing to do the same expansion. So we have C0 equals O10, same as the first term here, plus R10 O21. Okay, so that's the first two. Then we'll have R10 R21 O32 plus so on till we end up with R10 R21 R32 so on till Rn minus 1 n minus 2. This is just looking at this pattern for the first three terms help us to figure out this last term. And then on minus 1 plus okay, the last part, which is this part, the counterpart, this one is going to be R10, R21, R32, so on till Rn n minus 1 Cn. Okay, so turns out that this looks very complicated, but really there are two parts to it. This part, if you notice, has only O's in it, and that part corresponds to the net translation. This part is only the rotation. So the rotation formula is pretty simple. The translation one is the one which is complicated. Okay, and so if I give you a problem which has n frames, then you will have to sort of remember this mess consisting of this translation part and put it there. And there's a lot of, I mean, you can automate this, but there's unnecessary bookkeeping here on how to keep track of these rotation matrices. So what we'll do is I will show you actually a much simpler way of writing this combined rotation translation through what is known as homogeneous transformation. So let me finish this. This becomes complicated, right? So the solution is what is known as homogeneous transformation. Okay, so let me first define what a homogeneous transformation is and then show you how homogeneous transformation helps us to make this calculation much simpler. So homogeneous transformation. Okay, we'll denote the homogeneous transformation with the symbol H, and I'll write H I with respect to I minus 1, just like I wrote R10, R21. Similarly, this is transformation of HI with respect to frame I minus 1. It actually has 4 terms in it. There is Ri with respect to I minus 1, OI with respect to I minus 1, and then there are zeros and 1. So let's see how this looks. So first of all, the rotation matrix is, we've seen it's a 2 by 2 matrix. Okay, the location of point O, or the origin, is the x and the y coordinates. So it's 2, 1. Okay, so then this 0 is actually 1, 2. So it's basically 2 zeros, something like this. And then to make this matrix consistent, this 1 is simply 1, 1. So it's just 1. Okay, so that is the homogeneous transformation. Note that it has both parts to it, the rotation and the translation, as a single, which is combined in the matrix form. Okay, now what we'll do is, we wrote down the coordinates of C, the small c. I'm going to create a new variable called capital C, which is the small c and 1. Okay, so normally C is 2, 1. But because I added 1, it becomes 2, 1 and 1, 1. So this C is 3, 1. So by the way, this one is going to be 3, 3. So this is a 3, 3, and this is 3, 1. Okay, so now we are ready to write what is known as or use the homogeneous transformation. So if I want to write the coordinates of point C in frame I minus 1, okay, then I simply write it as I minus 1 times Ci. So remember that we wrote this for small c, right? Ci equals I minus 1 C. Sorry, I minus 1 is here I. So this is what we wrote down for pure rotations. This is looking very similar to pure rotation, except that there is a H matrix which actually incorporates the translation part. So if you expand this out, this will look like this. Okay, so these ones are actually placeholder. This whole row is a placeholder. This just makes the multiplication consistent. So now we can use this formula in this fashion. If you want to find the coordinates of C in frame 0, which is what we're interested in, the world frame, then all you do is you write the homogeneous transformations. That's it. You don't have to do any rotations, translation, sum it up. And that's why it's much simpler. Okay, now, how do you believe this is true? Well, let's just see if it actually works out for, let's see if this works out for n equals 2, right? So for n equals 2, we wrote down a formula, which is right here. So this is the formula for n equals 2. Let us try to see if we can get the same formula if we put n equals 2 in the homogeneous transformation formula. So let's just do that. Okay, so then the formula becomes C0 is H10, H21, C2. Okay, let's expand this out. C01 equals R10, O10, 0 and 1. And then we have R21, O1, sorry, O2, 1, 0, 1, and then C2, 1. Okay, let's keep the first term as it is and multiply the matrix times C21, so that will become R21. So the first row times the first column is what we get in the first row of the multiplied terms. So R21 times C2 plus O21 times this one. And then we have 0 times C2 plus 1 times 1. Okay, so this is R10, O10, 0, 1, R21, C2 plus O21, and then we have just 1. Okay, now let's multiply again to get R10 times R21, C2. So this is multiplying these two terms. Then we multiply, oh sorry, my bad. So I need to multiply this with this with O2 and add it. So O21, R10. Something is not right. I can't just swap the multiplication because matrix multiplication not commutative, my bad. So I should write this as R10, O21. So that's multiplying this with these two terms. Then I need to multiply O10 with 1. So O10. Let me just move this a little down. I think it gets a little confusing. Okay. So O10 times 1. And then we have 0 times anything is 0 plus 1 times 1 is 1. Okay, so now what you see is this first line here should be the same as what we got previously. So if you compare this with the term I wrote down earlier, well, I can pick this up. How do I copy this? I believe that's copy. And then if I stick it here, probably don't have space. Let's just try. Barely get it here. Maybe I'll put it here. Okay, so hopefully you can compare it now. You can see that the first term is the same as this term last term here, and then R1, yeah, it's the same, and then yeah, so it works out. So that works out for n equals 2, and you can try this for n equals 3, 4, and so on. So the key thing is to write this homogeneous transformation, and then multiplication is just a matter of combining these H matrices together in the right way. So always start with H10 all the way to manipulator. So what I'm going to show now is known as manipulator forward kinematics. Okay, so let me draw the manipulator. So the manipulator we're looking at is a two-linked manipulator, like so. It doesn't look that good. I need to make the length somewhat equal. Okay, so that's the manipulator. There's a pin joint here in the second link. Now, what we'll do is we will basically try to write this in terms of frames, right? So that we can use what we learned, homogeneous transformations, to represent the manipulator. So I'm going to first draw the base frame, which I will call O1, oh sorry, OO. O x0 y0, and let's say that the angle made by this link is theta1. So that's going to be the angle which describes the motion, the first link. And then I'm going to extend this first link and then show you the other angle, which is now the angle made by the second link with respect to the first one. Let's call these names. This is say P, this is Q. And what else? Okay, and then what we're going to do next is draw the frames. So because the frames is how we are going to write the homogeneous transformation. So let me say that this frame is x1, y1, and that frame is such that x1 is along the first link of the manipulator. Similarly, I'll draw frame 2, which is along the second link, and then y2. Okay, now I'm all set. My goal here is, so first of all, what is forward kinematics? Okay, so what the forward kinematics does is, given theta1 and theta2, so these links, and given the lengths of the manipulator, which I didn't draw here, but let's assume that the length of the manipulator is L1 and L2, it tries to find the coordinates of uh, P in global frame and Q in global frame. So forward kinematics means it basically gives you the end effector, which is Q, and the position of other links as needed. Okay, so what we'll do is now we will use this homogeneous transformation to write the position of P and Q based on the fact that we are given theta1 and theta2. So let's just do that. Okay, so we have, so we'll have to write P0 equals H10 P1, right? Because that's how we express the position of point P. We can also write the position of Q0 as H10 H21 Q2, right? Because Q is in frame 2 and P is in frame 1. So let's just expand this out. It basically comes down to R10, and then we need the coordinates of O1 with respect to 0. And then we just write it as P1 and P0. Similarly, for Q0, I need to write H10, which is R10, O10, 0, 1, and then H21, which is R21, 0, O21, 1, and then let me just write it as Q2. Okay, so now let's go about writing these transformations, rotation matrices, etc. down. So R10 is nothing but cosine theta 1 minus sine theta 1 sine theta 1 cosine theta 1. R21 is cosine theta 2 minus sine theta 2 sine theta 2 cosine theta 2. Okay, and then we need to write O10, which is basically, if you see here, O10 is the same as this point. Sorry, this is O1, my bad. O1 is this point because that's also the place where O1, X1, Y1 starts, right? So O1 is the same point as O0, which means that O10 is simply going to be the origin. It's not going to be anything different from the origin. Secondly, we need to write the position of O2 with respect to 1. So this is the coordinates of this point, which is also P. With respect to, this is, we'll call it O2, not O21. This is point O2, and we need to find the position of O2 with respect to frame 1, right? So that is going to be, so the position of O2 in frame 1, which is O1, X1, Y1, is basically L1, 0. Sorry. Yeah, it's L10. Why is it L10? It's because O2 is along the x1 axis. So its coordinate is going to be only that of, we'll only have an x coordinate to it, and the y coordinate is going to be 0 because its distance along the y1 axis is 0. Okay, so that gives me this, and then that. Okay, now we are only left with P1, which is, so this is capital P, this is the small p1, and then there will be uh, 1, right, by definition. So the coordinates of P in frame 1, in this frame, so that's again going to be the same as the coordinates of O2 in frame 1, which is going to be L1 along the x-axis, 0 along the y-axis, and 1 is this one, which is like a placeholder, which makes this multiplication consistent. So this one is from here, and these two are actually the P1 coordinates. Now let's write the coordinates of Q2. Okay, let's look at Q2. So Q is in frame 2. So we need to write the position of Q2 in its local frame. So it's going to again be along the x2 axis. So it will have a, so let me write that as Q21 first, and then that's going to be simply L2, 0, and 1, just like P1. Okay, so with that, we can now start expanding things out. I'm going to put all these things down in these formulas and write down P0 and Q0. So P0 is P0 comma and 1 equals R10, which is cosine theta 1 minus sine theta 1 sine theta 1 cosine theta 1. And then it was O10, so that's going to be 0, 0, and 1. And then P1 was L1, 0, 1. And so if you expand this out, you get L1 cosine theta 1, L1 sine theta 1, and 1. So that makes sense because if you look at the figure, the position of point P in frame OO x0, y0 is basically L1 cosine of theta 1, which will give you this projection along the x-axis, and then L1 sine theta 1 will give you the projection along the y-axis. Similarly, we can write the formula for Q0, which is going to be Q01. It consists of two homogeneous matrices. The first one is the same as the one I wrote down here. And then the second one is going to be cosine theta 2 sine theta 2 0 minus sine theta 2 cosine theta 2 0. And then we would have O21, which is going to be L1, 0, 1. And then finally, I write the coordinates of Q2 with respect to frame 1, which is L2, 0, 1. And so if you expand this out, you get, so there'd be multiplication and then there will be some simplification. You can use a trig identity to get L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2, L1 sine theta 1 plus. And then we have 1. So then what we really have to see is the first two lines, which is this. And that actually, again, if you look at the figure, it will make sense. The distance of, so the distance of point Q is going to be, well, first of all, we extend this. This is simply theta 1. So this complete angle is theta 1 plus theta 2. So if you want to find the position of point Q along the x-axis, you need to project this length along x-axis, so it will be L1 cosine theta 1 plus L2 times cosine theta 1 plus theta 2, which will be this length, ends over here. And so that will be the total distance along the x-axis, and a similar argument holds for the y-axis. So the homogeneous transformation in this case actually helps you to get this position in a very efficient manner. Okay, now the last thing before I stop is I'm going to show you MATLAB code which does exactly this and does a plot of the manipulator given L1, L2, theta 1, and theta 2, and I'll stop. Okay, so if I run this, then what will happen is it will show me a two link manipulator with the red link showing the first link, the blue one showing the second link, and this is for a specific value for L1 and L2. So it's the link lengths are 1 unit, and then theta 1, which is this angle made by the red link with the x-axis, is about 30 degrees or 0.5, and then the other one is 90 degrees to the red link. Okay, so that's the plot. And the question is, how do I get this? Well, what I did was I wrote down all these rotations and homogeneous transformations just like I wrote down on paper, and then I basically uh, found out the position of point P0, which is H01 times P1, and then for P, the location of point P, which is uh, the midpoint, is basically the first two elements. So I stored that in P. Similarly, I got the position of Q0, which now depends on two homogeneous transformation times Q2, which Q2 is the coordinate of Q in local frame. And then to get the coordinate of Q, the way I need it for plot is the first two elements of Q0. I got that. And then if you've gone through my MATLAB simulation, there is a MATLAB plot video, then you will see that one way of making these lines is to use the command line, and I basically specify the x coordinate of O, x coordinate of P, so that's the first and the endpoints of the red link, and then I give the y coordinate of the endpoints of the first link. Then I draw, and that's basically in the red color, and then I specify the x and y position of the second link. So x position is here, the y position is here, and then I specify that with the blue color, and then it just plots it. Now one thing you want to remember is you want to put grid on and axis equal, otherwise you will see that the figure will actually be skewed. So we can just drop this off and see what happens. Okay, you can see that it's like along the x-axis is 0.9 and along the y-axis 1.4 is the max extent, and so it doesn't quite look like a manipulator with equal lengths. So that's why you should always put axis equal, and that basically works a little bit well. It shows about 1.4 on the x-axis. The scaling is right, so it looks like it is of the same length, the two links. Now if you want to look more better, then you might want to put grid on. So now it draws those lines. And then if you want the axis to be a specific value, I specify the x limits to be -2 and 2, and same for the y, in which case they are basically from -2 to 2 and for the x and y. Okay, so I'll stop there. The next class I will take on this and show you how to do inverse kinematics, which is basically the inverse problem. Given a position for point Q, which is the tip, how do you find the necessary values for theta 1, theta 2? Okay, I'll see all of you on